Hello everybody. So let us continue with our discussions on the flow pattern identification by optical probes in microsystems. So in the last class I have already explained to you the principle of measurement and how it can identify the different patterns on the basis of the amount of light absorbed and scattered. Now we are going to see one particular application of this particular probe in microsystems. The reference of the paper from which this particular the workers who have taken this particular technique is also there, and you can refer to this for further reading. Here what do we find? We find that in this particular case 2 micro lasers are used. This is one thing we have to keep in mind, that the efficiency of this particular method will be dependent upon the intensity of light, because if the intensity of light is very high, then in this small volume whatever amount will be absorbed or attenuated can hardly be detected. So therefore, if the strength of the laser source is less, then it is going to be much more better, and in this particular case the researchers what they have used is they have used 2 micro laser beams, because they wanted to measure the velocity of the moving Taylor flux also. They have used 2 micro laser beams where the light passes through the glass tubes and the fluid at 2 different axial locations, and they have also used a pair of lenses, one lens for each particular source. This particular lens, it focuses the laser beam onto the middle of the microtube, so that we can understand the reflection, refraction etc. occurs in the center of the tube, and observing that we can know the cross sectional distribution of the voids. And on the diametrically opposite point 2 photodiodes are used, which record the intensity of light and the signals they are used to identify the different flow patterns, or rather the different distributions which happen in this particular case. And the signals, as we have seen in the previous case, the signals they are recorded by means of some particular data acquisition system, and in this particular case it's certain things are important. One is the lens and then the intensity of the light, and then a micro positioning system is also very important to align the laser beams with the lenses and the photodiodes, since everything is in a very miniaturized scale. So therefore accuracy, or much more accuracy, is necessary in this particular case. And in this case again the same thing as in macro system, the laser beam it interacts locally with the structure of the flow, and by suitable signal processing it is possible to determine not only the distribution of the phases, but also the velocity, the length, and also the frequency of the vapor bubbles. And so let us see the different type of signals which has been recorded. We need to remember one thing. In order to and one thing let me tell you, that the probe which had been developed in the multiphase flow laboratory, this particular probe it was developed for primarily for kerosene water systems. The need arose because none of the intrusive techniques could be used for oil water systems, because oil would stick to the water, to the probe, and then naturally after that we were unable to get any particular signals. The other thing is it was very effective for oil water, because the absorption coefficient of kerosene and water were very different, and these particular researchers they have used it for air water systems. Now when we are using it, it is very important to maintain a proper thresholding, such that we can identify the noises from the fluctuations. For example, we have to threshold it in such a way that we can identify that it is not a noise, but it is a bubble. So therefore in this particular case, what do we see? In air water system, when it is filled up with the liquid, then naturally a greater amount of signal is absorbed, and when it is filled up with the air, a lesser amount of signal is absorbed. So therefore the transmitted amount of light, or rather the incident amount of light on the photodiode, is going to be lower when water or any other liquid is in the predominant phase. It is going to be higher when gas is going to be, or gas comes on the path of the light. So, naturally if you observe the raw signals, what do we get? For bubbly flow pattern, more or less, since liquid is the predominant phase, we get an almost continuous signal at very low voltage. And whenever the bubble comes in the path of the light, we get small spikes which denote the passage of occasional bubbles of sizes smaller than the conduit diameter, which shows that liquid is the continuous phase and bubbles traverse this particular path. Now as we increase the flow rate and we approach the transition from the bubbly to the slug flow pattern, as we know it is marked by elongated bubbles, and this is immediately shown in the random signals that have been recorded. In this case, we find that the apparent difference between the bubbly and the slug flow, or rather the transition between bubbly slug flow, is immediately evident on comparing these two particular raw signals. Here we find that instead of almost steady signal at low voltage and a few spikes, the signal now exhibits alternating valleys and peaks, and we find that in the valleys some spikes are there which show the presence of gas bubbles in the continuous liquid slug, and the consistent peaks which we get, they show the passage of elongated bubbles. And in this particular peak region, the small disturbances which we get, they are due to the presence of the liquid film between the bubble and the conduit wall. We find that from the bubbly slug, as we approach the slug flow pattern, we find the intermittent pattern is very clear. And more importantly, I would like to say that since the liquid slugs are almost unaerated, so as a result what happens, we find that it is almost a square wave type of a signal. If the noises can be eliminated, it becomes almost a square wave type of a signal, where we can very well see large peaks and small tapered valleys, which naturally shows that now large Taylor bubbles and short liquid slugs are passing through the, or rather are traversing the path of the laser ray or the laser narrow beam. Now, if we compare this particular signal with the bubbly slug signal, certain things are evident. Number one, that the proportion of the gas phase has increased because the signal now lies for a greater portion of time in the higher voltage region. Secondly, more or less all the bubbles are elongated bubbles, and thirdly, there are lesser disturbances in the liquid slug. So, therefore, from this it is the comparison immediately shows us how erratic the transition zone was compared to the fully developed zone. Now, as we go for higher velocities, what people observed were, I would like to tell you that in microchannels your annular flow is not very evident, and this particular group of researchers, they also approach something like the slug or the semi-annular flow pattern with occasional liquid bridging. They could not approach and they could not get a pure annular flow. How is this evident? If you observe this particular signal, the transition from slug to annular or semi-annular, whatever you say, we find that for now the signal is for a greater fraction of time, it is in the high voltage area. So, that shows that definitely gas is passing the flow passage, or gas is traversing the path of light for a greater fraction of time, and there are short spikes in the opposite direction, which shows that the rear bubble, it is getting deformed, or maybe some amount of smaller satellite bubbles are getting shedded from the rear bubbles, as a result of which there are some spikes in the downward direction when short liquid slugs come in the path. So, if you just compare this particular your signal with the bubbly signal, you will see that both of them are almost mirror images, and this shows that air is the predominant phase in this particular case and water was the predominant phase here, and in the intermediate region comprising of bubbly slug and slug flow, both of them were more or less comparable, with water being a larger proportion here, air being in a larger proportion in this particular case. So, therefore, in this particular way we find that the optical probe was one particular technique which was used quite, or rather which has been used with some particular success in microchannels. Now, the next technique which has also been used to some extent in microsystems is the impedance probe technique. What do we observe in the impedance probe technique? What does it do exactly? It is quite a popular technique in macro systems. The reason for its popularity being, firstly, it is cheap, it gives an instantaneous response, and it can be fabricated in a large number of designs in order to suit whatever purpose we want to serve. And therefore, the impedance probe, it is the second most widely used method, not only for void fraction measurement, but also for the estimation of void fraction, or rather void distribution. Now, what does it do basically? It basically measures the difference in electrical conductivity or electrical impedance of the two-phase mixture. Okay. So, therefore, in this particular case, what happens is it measures the electrical impedance or the electrical means the thing is that when there is a two-phase mixture flowing, then and we have two electrodes may be located at the two walls, then the electrical path is through the two-phase mixture, or rather it is through the fluid medium. So, therefore, in this particular case, the resulting admittance, it is more or less it is a function of your, it is the reciprocal of electrical impedance. It is the reciprocal of electrical impedance, and this particular admittance, or A if we call it, this particular admittance, it is going to be a function of firstly the specific conductance of the intervening medium, which in case of two-phase flow is the specific conductance of the individual phases. Then it is also a function of electrical permittivity, or in other words, it is a function of the electrical properties of the two phases. Then it is also a function of void fraction and your flow pattern, right. So, therefore, we find that in this particular case, the thing which happens is that suppose we have any particular probe, then the depending upon the composition of, or rather depending upon what are the two phases which are present here, the net electrical admittance is usually measured, and this electrical admittance, this is the inverse of electrical impedance of the two-phase mixture, and this is a function of the material properties which are nothing but the specific conductance of the individual phases and the electrical permittivity. It is also a function of void fraction and flow pattern, right. Now, if the two phases are fixed, so naturally the material properties become fixed, and in that case it is just a function of void fraction and flow pattern. It is a coupled function for one particular flow pattern. It has got some specific relationship with void fraction, and so if the flow pattern is known, then we can find out, we can have an estimate of void fraction from the admittance, which can be either the conductance or the capacitance of the two-phase mixture. But in order to measure void fraction from admittance, we need to have an a priori knowledge of the flow pattern, right. and this particular specific conductance this determines the conductive reactance, while permittivity determines the capacitive reactance. So, it means that if we are operating in the conductance mode or in the conductivity mode, then the specific conductance of the two phases will be determining the conductive reactance, while if we are operating in the capacitive mode, then permittivity will be determining the capacitive resistance. Now, for a given geometry, what we find is that the measured admittance, if it is appropriately normalized, this will be a function of void fraction and your flow pattern. So, therefore, the next thing is that once this particular specific conductance, so the principle of measurement is that we have two electrodes on two sides of say any particular channel, right, and between this whatever is the composition and the distribution, depending on that we would be getting some particular signal. The signal can be due to the difference in the conductivity of the two phases. It can also be due to a difference in the dielectric constant or permittivity of the two phases. We have to decide which particular property we would like to exploit depending upon the system, and then we have to work accordingly. For example, if it is a kerosene air mixture, of course, for that possibly we will not be using electrical or impedance probe, but for that case a conductivity meter or a conductivity probe is not going to serve the purpose, because both of them are more or less non-conducting. But for a air water system, conductivity probe is a very efficient and a very widely used technique, because air and water have widely different electrical conductivities. Well, so the advantages which we have are, number one, the low cost technique. Then the other thing is it is very suitable for transient measurement, because what it does is more or less it gives us a time varying voltage signal across across a resistor. The basic principle is that from here more or less the current which is passing through this, that is passed through a known resistor, and the voltage across the resistor is measured, and this is then recorded as a function of time, and this gives us an idea about the current which was passing, and this current is a function of the composition of the two phase mixture. So, therefore, it is quite suitable for transient measurements, and as I have already said, the large variations of electrode design is possible. Now, usually it can be intrusive, it can be non-intrusive as well. How mostly it is intrusive, where what we have is, we have maybe one particular electrode which is immersed here, and maybe the wall is another electrode, or maybe we can have two electrodes of slightly different dimensions, where the current between the two is measured, and the circuit is closed when water comes in contact with the two electrodes, and when moment a bubble comes in contact, the circuit is broken, and that is shown by a drop in voltage, and from recording those drops we can find out a distribution. So, anyhow, so this is quite an attractive technique, and mostly for the micro channels, the capacitance probe technique has been used. Now, the capacitance probe, although this circuit is not very, it is slightly more complicated, but there are certain advantages of the capacitance probe. Firstly, if we have to make any particular quantitative measurement, how the signals are recorded is that just recording the signals just from the voltage time signal, we are not going to get anything unless it is properly normalized. Now, how is it normalized? Initially, what is done? The voltage when the system is full of water is recorded, say this signal is VW, and then the voltage for the flow passage completely empty or for air flow is recorded. So, therefore, we know the two extremes when the circuit was closed and when the circuit is completely open. Now, when we record the voltage signal during air water flow, it is going to lie between the two. So, therefore, this particular signal, it is normalized as V minus V air by VW minus V air. This is the normalized voltage, this is a function of time. So, naturally in this way we get the normalized voltage, and this is the voltage which is measured as a function of time in order to obtain the void fraction data. So, therefore, it is quite evident that this particular normalized voltage signal, from where we would want to have data on alpha, or we would like to find out the distribution of the two phases, that definitely depends upon the voltage which we receive when the test passage is full of water, and naturally, so it depends upon the conductivity of the liquid which is there inside. Now, we know that conductivity is quite sensitive to the amount of impurity, to temperature, etc., etc. So, therefore, almost for every experimental run the conductivity can be different, and so therefore, if any particular measurement is highly based on the liquid conductivity, and if the liquid conductivity is changing so much, then in that case normalization or getting, if we just want to have an idea regarding the qualitative nature of this signal and to identify flow patterns, it is fine. But if we really want to have some quantitative idea regarding the estimation of void fraction or the in situ composition, then this dependence of conductivity on several other extraneous parameters which are not under our control becomes slightly difficult. So, naturally, when we are operating in the capacitance mode, the first advantage is it is less sensitive to changes in liquid conductivity. The other thing is relative permittivity of water is not affected by ionic conduction, which again means the same thing. And definitely it is simple and low cost, it can withstand severe environmental conditions, and the important part is the design which has been used in literature. What they use, it is a modified version of the arc electrode probe. What the arc electrode probes does, it has two electrodes which are flush mounted with the wall of the conduit, and by means of electrical lines of forces between the two arcs, it measures the effective conductivity of the two phase mixture. So, therefore, this is something quite commonly used in macro systems, and one particular group of researchers, this is the thing which I was telling, that while we are using arc electrode probes, there are two electrodes which are flush mounted. Now, in this particular case, a few problems arise. First thing is, there is a fringing effect near the edges, and the two arcs cannot be brought very close to one another. So, therefore, this fringing effect it exists. Now, to eliminate this, a very frequent thing which is done is to use two guard electrodes at the two ends, so that the fringing effects are taken care of by them, and more or less the measurement zone is free of this. And the electrostatics thing, it is there, and there is no point in going into great details from here, but from this particular slide we can understand how the current can be expressed in terms of the current density, voltage and all those things. And so a variation of this arc electrode probe has been used by this particular group of researchers. What they have done? They have used a rectangular microchannel, and in this particular rectangular microchannel they have used two stainless steel electrodes which are embedded in the base plates. Okay. And these two stainless steel electrodes are such that the faces of the electrodes are flush mounted with the two walls. A better way to represent is this, as you can observe that this is the channel and the two stainless steel electrodes, they are flush mounted with the two edges of the, or rather of the two walls of the channel, such that it can measure the electric field between the two electrodes, right. And in this case also an auto balancing bridge method is used, as I have already mentioned. In this particular auto balancing bridge, what is done is there is an, and since it operates in the capacitance mode, so therefore an exciter signal is passed, and then this particular current which moves to the test cell, it is sent through a reference resistor, and then from the reference resistor the voltage across the reference resistor is measured, and that gives us an idea regarding the amount of current which was flowing through this particular cell. And along with the raw signal, attempts were also made, just like other researchers, in order to perform the probability density function analysis of the signal, such that we can obtain a better idea regarding the flow distribution. So, we are going to discuss it in the next class. We continue our discussions on experimental techniques of flow pattern measurement and void fraction measurement in the next class. Thank you very much.